Hello everyone, and welcome. Today, we're diving deep into a fascinating paper from DeepSeek-AI that introduces DeepSeek-R1, a cutting-edge large language model designed to excel at complex reasoning tasks. We'll explore how they leverage reinforcement learning in innovative ways to achieve impressive results. We'll cover a lot of ground today, so here's a roadmap. We'll start with the context and DeepSeek-AI's key contributions, then unpack their three-pronged approach, DeepSeek-R1-0, DeepSeek-R1, and their distillation technique for smaller models. We'll then analyze the experimental results, discuss the broader implications, and look at future research directions. Large language models have come a long way, generating human-quality text and even code. However, true reasoning, the ability to solve complex problems step by step, remains a challenge. While techniques like chain-of-thought prompting offer some improvements, they're not a complete solution. This paper explores how reinforcement learning can be used to directly incentivize reasoning abilities within LLMs, leading to the development of DeepSeek-R1-0 and DeepSeek-R1. This research makes several significant contributions. First, DeepSeek-R1-0 demonstrates that pure reinforcement learning, without any supervised fine-tuning, can significantly improve reasoning abilities. Second, DeepSeek-R1 introduces a novel multi-stage training pipeline that combines cold start data, reinforcement learning, and supervised fine-tuning for even better performance. Third, they've successfully distilled these reasoning capabilities into smaller, more efficient Quen and Llama models, making the technology more accessible. Finally, they've open-sourced their models and data, fostering further research and collaboration within the community. The results speak for themselves. DeepSeek-R1 achieves state-of-the-art performance on challenging reasoning benchmarks like AIME 2024 for Math 500, and Codeforces for coding. It also demonstrates strong knowledge and understanding on benchmarks like MMLU, MMLU Pro, and GPQA Diamond. Beyond reasoning, it excels in creative writing, general question answering, and tasks requiring long context understanding, achieving high win rates on AlpacaEvil 2.0 and ArenaHard. The key innovation here is moving beyond the traditional reliance on massive supervised datasets. DeepSeek-AI shows that large-scale reinforcement learning can be incredibly effective for developing reasoning abilities, even without initial supervised fine-tuning. They also demonstrate how a small amount of strategically chosen cold start data can further boost performance. We'll now look at their three main approaches in detail. DeepSeek-R1-0 is a fascinating experiment in pure reinforcement learning. Starting with the DeepSeek-AI v3R base model, they use the GRPO algorithm and a reward model that focuses on both the accuracy of the final answer and the correct formatting of the output. The special training template, using think and answer tags, encourages the model to explicitly generate its reasoning process, which is crucial for improving its reasoning abilities. GRPO, or Group Relative Policy Optimization, is a key component of DeepSeek-R1-0. It's a critic-free reinforcement learning algorithm, meaning it doesn't require a separate critic model, making it more efficient. It estimates the baseline from group scores, simplifying the training process. The objective function, shown here, aims to maximize rewards while also controlling the policy's divergence from a reference policy. What's truly remarkable about DeepSeek-R1-0 is its self-evolution during training. The model learns to allocate more computational resources to thinking, generating longer and more complex chains of thought, which directly translates to improved performance. Researchers also observed intriguing aha moments where the model re-evaluates its initial approach, demonstrating a form of reflection and leading to more effective problem-solving. The paper provides specific examples of this behavior. DeepSeek-R1 builds upon the success of DeepSeek-R1-0 by incorporating a cold start. This involves fine-tuning the base model on a small, carefully curated dataset of high-quality chain-of-thought examples. This cold start improves the model's initial readability and provides a stronger foundation for subsequent reinforcement learning. They then apply reasoning-oriented RL, similar to DeepSeek-R1-0, but add a language consistency reward to prevent language mixing. Finally, they use rejection sampling and supervised fine-tuning on a larger, combined dataset to further refine the model's performance and generalize its capabilities. To make this powerful reasoning technology more accessible, DeepSeek-AI distilled the knowledge from DeepSeek-R1 into smaller Qwen and Llama models. This is done by fine-tuning the smaller models on the data generated by DeepSeek-R1, effectively transferring its reasoning abilities. This distillation process is crucial for deploying these models in resource-constrained environments. The models were rigorously evaluated on a wide range of benchmarks, covering reasoning, knowledge, coding, and open-ended generation tasks. These benchmarks include MMLU, C-Evil, Code Forces, AIME, and many others, providing a comprehensive assessment of the model's capabilities. They were compared against strong baselines, including previous DeepSeek models, other open-source models, and closed-source models like GPT-4, using various evaluation metrics like pass at K, consensus at 64, EM, F1, and ELO rating. DeepSeek-R1 significantly outperforms its predecessor, DeepSeek-AI v3, and other baselines on many reasoning and knowledge benchmarks. Impressively, it achieves performance comparable to OpenAI's o1-1217 on several tasks. Its strengths lie in code generation, math problem solving, and long context understanding, demonstrating the effectiveness of the combined RL and SFT approach. The paper provides detailed tables with specific results across all benchmarks. The distilled models, particularly the 14B, 32B, and 70B parameter versions, also show substantial improvements in reasoning abilities. They outperform other open-source models, proving that the distillation process effectively transfers the reasoning knowledge from the larger DeepSeek-R1 model. The paper includes detailed tables comparing the performance of different distilled model sizes. A key takeaway from this research is that distillation is a highly efficient and effective method for improving reasoning in smaller models. It's more practical than directly applying large-scale reinforcement learning to smaller models, which can be computationally expensive and may not yield the same level of improvement. However, for pushing the absolute limits of LLM reasoning, larger base models and more advanced RL techniques will likely still be necessary. The DeepSeek-AI team also explored other promising approaches, such as process reward models, PRM, and Monte Carlo tree search, MCTS. However, they encountered challenges in scaling these methods effectively for large language model training. PRM faced difficulties in defining fine-grained reasoning steps and suffered from reward hacking. MCTS struggled with the vast search space of token generation and the complexity of training a reliable value model. While DeepSeek-R1 demonstrates impressive capabilities, it still has limitations in areas like function calling, multi-turn dialogue, complex role-playing, and structured output like JSON. It also exhibits some language mixing issues with queries in languages other than English and Chinese, and its performance can be sensitive to prompt phrasing. Future work will focus on addressing these limitations, exploring the role of long chain-of-thought reasoning in improving general capabilities and enhancing performance on software engineering tasks. DeepSeek-R1 represents a significant advancement in LLM reasoning. DeepSeek-R1-0 showcases the potential of pure reinforcement learning, while DeepSeek-R1 achieves state-of-the-art performance through its innovative multi-stage training pipeline. Distillation provides a practical way to transfer these capabilities to smaller, more accessible models. This research opens up exciting new directions for future work, paving the way for even more powerful and versatile language models.